All right, team, the second part of our video lessons will start on page 8. It's right after our log equations that we were just solving. So we're going to look at a few graphs here. There's a lot of information, a lot of graphing that we've done in the past that we're going to draw on, transformations and tables, and we're really going to build on this. I think logarithms are tricky to graph, but once you figure out the routine, they're just like any other graph. So as logarithms and exponentials are inverses of one another, we will see how they are similar in structure, but note that there is a swapped domain and range. We know that as inverses, that's what the domain and range will do. Key features are still important for us. Let's see what we can do with a basic logarithmic graph. So here we see y equals log base 4 of x. And here's my recommendation on how to approach this. Because we have some domain issues, this stuff needs to be positive, it can't be 0, it can't be negative. So what I've found is the most effective way to graph these is to convert to exponential form. You'll see that in exponential form, it looks familiar, just x and y are swapped. That's literally what an inverse does. So we're going to graph this just like we would graph an exponential. However, because it's tricky to plug in x values in for a logarithm, we need to have compatible figures. What we do to graph a logarithm is plug in to the y values. When we plug those in, right, and we use this modified equation, we're going to get some familiar seeming values, right? 1 over 16, 1 over 4, 1, 4, and 16. We can see here that x and y have literally swapped places from those exponentials that we did way back at the beginning of the unit. So we have some points here. We can plot these. Just be careful. 1 over 16 is going to be very close to the y-axis, but down at -2. 1/4 is going to fit here. And then we get 1, 0, 4, 1, and 16, 2 won't quite fit on our graph. So what you're going to notice here when we connect our dots, right, this is going to behave asymptotically. That asymptote is at x equals 0. And this should feel at least vaguely familiar, right? We've seen these type of asymptotes before. It's just with an exponential function. In this case, we're dealing with a logarithm. So we know that in an exponential function, its domain would be infinite. Well, that will be the range of a logarithm. We know that the range of an exponential depends on the asymptote, and what we see here is that we have a vertical asymptote at x equals 0, so the domain of this logarithm will depend on that asymptote. It will go from 0 to infinity. That asymptote is at 0. X equals 0. So the end behavior gets a little tricky. We can see that even though it's slowing down, as x gets larger and larger, so will f of x. So it will rise to infinity. However, our domain is restricted on our the left side of our graph. So what we will say is that as x goes to negative infinity, f of x does not exist, DNE. Right? There's just no end behavior in that direction. So what's different with a logarithmic graph? We plug in the outputs and get out the inputs. We flip forms, we move to exponential form, and then we graph it almost the same way we would an exponential. We just plug in for y. All right, we have 2 more graphs on the next page. The next one has our old friend, the natural log here. So that's our base e. That does make things a little tricky. But what we're going to try to do here is we are going to take e to the y equals x, right? That would be the exponential form, right, without the transformations. And then what we would do to that graph is we would move left 4 and down 3. Well, let's just see what happens if we start a table. just like where am I plugging in? I'm plugging into this form of the equation, and I'm plugging in for y. And what I would plug in here, I would plug in our basic, normal, regular -2 to +2 values, right? -2, -1, 0, 1, 2. But we are experts with transformations, and we know that moving down 3, well, all of our y values are going to subtract 3. Now our x values, we'll have to figure them out. Now when we plug in -2 for y, we end up with 1 over e squared. But if we want to move this left 4 units, we're going to subtract 4 from that x value. We're going to get 1 over e minus 4, 1 minus 4, e minus 4, and finally e squared minus 4. I know that we're not the most comfortable with values of e. We know that e is approximately 2.71. So when I approximate it, I treat it like it's about 3 and then, just kind of ballpark it down a little bit. So if we were to sketch this, we know that if everything has moved to the left, we now have a vertical asymptote at x equals -4. So I'm going to start by sketching that, right? -4. And then that table that includes those transformations, well, we have some points. If we consider e to be about 3, 1 over e squared is, about 1 over 8.5. That's, about 0.12, somewhere in that range. Well, if we subtract 4 from that, we get really, really close to -4. So close to -4, decimal close to -4, the y value, -5. There's our first point. 1 over e, call it 1/3, minus 4, that's going to be about -3.7. And we move up 1 y coordinate, we're about there. 1 minus 3 gets us to -3. That gets us a little easier. That's going to be right here. And -3 is the coordinate of that point. E is about 2.7, minus 4 would be at about -1.3. And that would put our next point right about there. And e squared, let's call it about 8.5, minus 4 would be about 4.5. So 4.5 and -1 right there. I know that this is a little trickier to approximate the value of e. I don't know if we're all the most comfortable with it. But this would likely not be a calculator problem just because you can graph using your calculator. Let's finish it up with the end behavior here. As we go to the right, our graph would continue growing. So we would rise to infinity. And as we go to the left, well, the function does not exist. Oh, we didn't talk about domain and range. Our domain depends on the asymptote. It will go from -4 to infinity. And the range will be infinite, -infinity to infinity. All right, we have one more graph that we're going to look at. And this one's going to be a little bit trickier. We have to identify some transformations. So the base here is 10. So we're going to treat, kind of as our default table, right? X equals 10 to the y, right? That would be if there were no transformations, and what we'd have for x and y, we'd go -2, -1, 0, 1, 2, 1 100th, 1/10th, 1, 10, and 100. Well, that would be the parent function, and then we have to apply some transformations. I find these transformations to be frustrating when we have multiple horizontal. But if we follow reverse order of operations, or if we wanted to undo this, we would go right 6, and then horizontally compress by 1/2. There's also a vertical reflection. So that's going to make a pretty significant change to our tables. If we want to go right 6, we're going to take our x values and add 6 to them. And then if we want to horizontally compress them by 1/2, we're going to put that 1/2 right here. The vertical reflection, we're going to take those y values from the table on the left, and we're going to flip their sign. That one's easier, so we can start there. All right, so what we're doing is we're transforming this table, and those transformations are visible with the 1/2 and the +6, as well as the negative. So with our y values, -2 becomes 2, -1 becomes 1, 0 stays the same, 1 becomes -1, and 2 becomes -2. Over on the left-hand side, a little bit trickier. We add 6 to our x quantity and then divide it in half. We would get 6.001 divided by 2. Our y value would be 3.0005. If we were to add 1/10, if we were to add 6, we would get 6.1. Oh, I think I added one too many zeros in the previous one. We would have 6.1. We divide that in half, and we get 3.05. If we were to plug in, if I were to take 1, add 6 to it, and then divide by 2, I would get 3.5. If I were to take 10, add 6 and divide by 2, I would get 8. And if I were to do the same thing with 100, I would get 53. So what have we done to create these values? We've observed the transformations available on the function. We've transformed a modified form of our function over here on the left. Right? We plug into our y values and then apply those transformations like we did back in Unit 1. So these are our points. Let's plot what we have here. We can see that at 3.005 and +2, we have a point. 3.05 and 1, we have a point. 3.5 and 0. 8 and -1. 6, 7, 8. We can see that this asymptote would be at the line x equals 3, and we can connect those dots, right, with our vertically reflected logarithmic function here, looking something like that. So let's finish up the key features and call it a day. The domain here, again, depends on the asymptote. The asymptote is at x equals 3. So if we're moving to the right of that, it's going to go from 3 to infinity. The range, free money, it is infinite. And the end behavior, well, as we go to the right, we'll keep becoming more and more negative. So we would fall to negative infinity. And as we go to the left, there's nothing going on there. So there is no end behavior. We have one more problem. Excuse me, I overlooked example 24. Our last problem here, we are going to create a logarithmic function. I'm going to call it g of x. Right? We have f of x. It is log base 2 of x. We want to construct a function that has a vertical stretch of 3. Now let me do some colors here. A vertical stretch of 3, a vertical shift of 3, and a vertical asymptote at 4. Well, we know that our base function is going to be log base 2 of x. Well, if I want to move this to the right, I'm going to put a -4 in the parentheses. We've dealt with our vertical asymptote. If we want a vertical shift, that's going to be +3 on the outside. And a vertical stretch, we are going to multiply by 3. So our function here will be 3 times log base 2 of the quantity x minus 4 plus 3. That wraps us up for part 2 of our video. Thanks, everybody.